Hello students, welcome to my channel Arun's Physics Portal. In this lecture, I will be talking about emitter-coupled logic. This topic is meant for MSc students of Physics and Electronics and also for BE and BTech students of EEE and EC branches. The research scholars will also find this topic useful. The complete note of the topic is given here for your convenience. I hope you enjoy going through it. Now let us come to the topic. The emitter-coupled logic or ECL is the fastest logic family and finds application where speed is of prime importance. High speed is achieved in ECL by using transistors in difference amplifier configuration so that they do not operate either fully saturated or cut off, but operate between cutoff and active regions, thereby eliminating the storage time. The adverse effect of diffusion capacitance is thus eliminated. Since in the difference amplifier configuration, the emitters of the two transistors are coupled together, it is referred to as emitter-coupled logic. The emitter-coupled logic family is characterized by very high speed, high fan-out capabilities, low noise generation, complementary output, high cost, and incompatible with other logic families. A basic ECL circuit for two input positive OR oblique NOR gate is shown in figure 1. There is a basic difference between ECL and all other logic families as far as the supply voltage is concerned. In ECL, we see that the positive end of the supply, it is connected to ground, whereas in all other logic families, the negative end of the supply is grounded. This is simply done to protect the gate from an accidental short circuit and also to minimize the effect of noise induced in the power supply. Okay? Such a gate is made by using positive logic, where logic 1 is represented by minus 0.7 volt, which is less negative, and logic 0 by minus 1.55 volt, which is more negative. In negative logic, the functions would be AND oblique NAND. A reference voltage of minus 1.29 volt is applied at the base of transistor Q3, and the circuit operates from VEE equal to minus 5.2 volt. Before I explain how it operates, it is advisable that you draw this figure on your copy so that when I explain it, you can follow what is being said. Okay? Figure 2 gives you the circuit symbol of a two-input ECL or oblique NOR gate. So now let us explain how the circuit operates. So refer to the figure 1. The first case we consider is when both the inputs A and B are at logic 0 state, that is at minus 1.55 volt. We assume that the transistors Q1 and Q2 are cut off and Q3 is conducting in the active region. This is our assumption. We'll show that this assumption is correct. So what is VE? VE is the potential at the emitter of transistors Q1, Q2 and Q3, which are connected together. Okay, so VE is equal to VR. What is VR? VR is the potential applied at the base of transistor Q3. Okay, minus VBE3. So VR is the potential applied at the base of transistor Q3. So this is minus 1.29 volt. Okay, VBE3 is the potential between the base and emitter of transistor Q3, which is conducting as we have assumed. So this potential will be equal to 0.7 volt, because for a conducting transistor, the base emitter voltage must be 0.7 volt. So this difference is minus 1.29 volt minus 0.7 volt. So this is minus 1.99 volt. The emitter current is IE is equal to VE minus VEE upon R1. V, as we have seen, this is equal to minus 1.99 volt, and VEE is the applied voltage, and this is equal to minus 5.2 volt. R1 is 1.18 kilo ohm. So this gives you the value of emitter current as 2.72 milliampere. Since in any transistor, the collector current and emitter current are nearly equal, we can infer that the collector current of transistor Q3, which is IC3, is also equal to 2.72 milliampere. Therefore, the voltage and the collector of transistor Q3 is Vc3, and the collector of the transistor Q3 is connected to the base of transistor Q4. So these two volt potentials will be equal. So we have Vc3, the potential at the collector of transistor Q3, equal to potential at the base of transistor Q4 is equal to minus IC3 into R5. Okay, so IC3 is 2.72 milliampere, R5 is 300 ohm, so this is 0.3 kilo ohm. So this gives you value of Vc3 equal to Vb4 equal to minus 0.82 ohm. Okay, I am going to show that transistor Q3 is actually conducting as we have assumed earlier. So Vc3, the collector potential of transistor Q3 is minus 0.82 volt. Its base potential is minus 1.29 volt, and therefore the collector base potential is Vc3 minus Vb3 is minus 0.82 volt minus 1.29 volt. So Vcb3 is 0.47 volt. So Q3 collector junction is reverse biased, which is necessary for a transistor to conduct. Again, Vbe3, the base emitter potential of transistor Q3 is Vb3 minus Ve3. This is equal to minus 1.29 volt minus 1.99 volt. So this is 0.7 volt. So the emitter junction of transistor Q3 is forward biased, and therefore the transistor Q3 has forward biased emitter junction and reverse biased collector junction. So therefore it will conduct. Okay. So the output Y1 will be, Y1 is, see the figure, it is Vc3 minus Vbe4. So this is minus 0.82 volt minus 0.7 volt. So this is equal to minus 1.52 volt, which represents logic 0. Hence, if all the inputs are at minus 1.55 volt, base to emitter voltage of input transistors is Vbe1, which is also equal to Vbe2. This is Vb1 minus Ve, or you can also write it as Vb2 minus Ve. This is equal to minus 1.55 volt minus 1.99 volt. So this is plus 0.44 volt. Since base emitter voltage is less than the cut-in voltage, the transistors Q1 and Q2 remain cut off as we have assumed earlier. We have also shown you that transistor Q3 actually conducts. The base and emitter of transistor Q5 are effectively at the same potential. You see from the figure, we have the collectors of Q1 transistor and Q2 transistor connected together, and this is connected to the base of transistor Q5. Note that since transistor Q1 and Q2 are not conducting, the current IC1 is 0, and therefore there is no potential drop across the resistance R4. So the collectors of Q1 and Q2 transistors are at 0 potential because it is connected to the ground, and therefore the base of transistor Q5 is also at ground potential. The base and emitter of transistor Q5 are effectively at the same potential, that is, they are at the ground potential, and therefore it behaves like a diode. The voltage at its emitter is therefore minus 0.7 volt, which is assumed to be logic 1. Hence, Y1 and Y2 are complementary. Okay. We now consider the second case, that is when at least one input, say A, is high. In this case, the transistor Q1 conducts, Let us assume that the transistor Q3 is cut off. Now VE is VA minus VBE1. So this is minus VA is minus 0.7 volt. VBE1 is minus 0.7 volt. So this is minus 1.4 volt. Hence VBE3 is VR minus VE is equal to minus 1.29 volt minus 1.4 volt. So this, for these differences, you refer to the figure 1. So this is plus 0.11 volt, which is less than the cut-in voltage of the transistor Q1 or Q2. So this is less than 0.7 volt, which confirms our assumption that the transistor Q3 is cut off. Now IC1 is equal to VE minus VEE upon R1. VE is minus 1.4 volt and VEE is minus 5.2 volt. So the numerator is minus 1.4 volt minus 5.2 volt divided by 1.18 kilo ohm. So this gives you the value of IC1 as 3.2 milliampere. Now we have IC1 is equal to 3.2 milliampere, whereas IC3 was found to be 2.72 milliampere. Since the potential at the collector of transistor Q1 or Q2 when it is conducting must be equal to the potential at the collector of transistor Q3 when it is conducting, we must have IC2 into R4 equal to IC3 into R5, and this must be a constant. So if IC3 is less than IC2, it is obvious that R4 must be greater than R5. Okay. Now VC2 is equal to minus R4 into IC1, and this is equal to minus 267 ohm into 3.2 milliampere. So this is minus 0.85 volt. Therefore, the output taken from the emitter of transistor Q5 is Y2 is equal to minus 0.85 volt minus 0.7 volt. So this is equal to minus 1.55 volt, which corresponds to logic 0. Hence the circuit shown in figure 1 performs the OR oblique NOR operation. In table 1 here we have shown some specification for ECL. So power supply required is 5.2 volt, power dissipation is 50 milliwatt, propagation delay is 1 nanosecond, fan in is 5, fan out is 25, and noise margin is 0.4 volt. So this is all about the emitter coupled logic. I assume that you like this presentation. यदि आपको मेरा यह प्रेजेंटेशन अच्छा लगा हो तो इसे लाइक करें, शेयर करें और मेरे चैनल को सब्सक्राइब करें. So thank you for watching. See you next time with some other topic of interest. Till then, goodbye.